Welcome viewers. In this video we'll see the introduction about shift register in digital electronics. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic shift register. Register is a combination of flip-flop. Work is to store the digital data of any kind. So the registers are made up of flip-flop. We know that flip-flop is a temporary storage element that will store a single bit. So by using flip-flop, the register is constructed in order to store the digital data. And shifting also possible on application of the clock pulse, right? So we can store the data, and another application is shifting the data, that is data storage and data movement. We can move the data from right side to left side or left side to right side, serial, parallel, all are possible. The storage capacity of register is the total number of ones and zeros in the data, right? So the capacity is nothing but ones and zeros, right? In that we see the shift register. What is mean by shift register and what are the types are available? The movement of data from stage to stage within the register or into or out of the register upon the application of the clock pulse. So we can move the data from stage to stage within the register or into the register or out of the register. That is called here by applying the clock pulse. So based on that, the types of data movement in the shift registers are, there are various types available. We'll see the types one by one. The first type is serial in, serial out type. SISO. Data is entered serially and out by serially. See this input data. So this box refers the register. This is register 1, 2, 3, 4. There is nothing but flip-flop constructed by flip-flop. This is a 4-bit register. So the data is given serially and it is passing also serially from one register to another register. Similarly here it is given from left side. This is given from right side. So it is called a right shift register. This is called a left shift register. The left side input is given and is moving in a serial manner, and right side the output is available. Right. So that it is called a left shift register. This is right shift register. Serially data is given and serially data is going out. I will go to the next type. So the second type is serial in, parallel out. SIPO. See, these data are entered serially and data are out by the parallel. Parallelly it is going out. Right. Previous one, serial input, serial output. This is serially in. Data are given serially, but the data are taken as parallelly. Right. Then the third type, parallel in and parallel out. PIPO. So data is given parallel and data taken as a parallel also. So this we already explained. These boxes refers the register, flip-flop. Right. So earlier we give serial and serial in, serial out. Second type, serial and parallel out. This is parallel in, parallel out. Data is given parallelly and data is taken also parallelly. PIPO. Next one, parallel in, serial out. The fourth type is the parallel in, serial out. So parallelly data are loaded, but is data are taken out by serially. Right? According to our requirement, we can use either any one of the types, serial in or serial out, serial in parallel, parallel in, parallel out, or parallel in, serial out. So this is the 4 basic types, and another 2 more types available, bidirectional. So the data moving from right side to left side or left side to right side, bidirectional. Both that sides are possible. Earlier we discussed only one direction, left shift register, right shift register. But this register were both bidirectional. Serially we can move from right to left or left to right. So this is called a bidirectional. And another 2 more types available, rotational right, rotational left. See, the data are moving serially. The last data again it is connected to the input side, right side. So it is rotating right side. Here the data is given left, moving left side. The last data is again given as a input. So it is rotating. So it is nothing but a rotating. We know that some name boards and names are rotating, no? Like this will be rotated. So this will be rotating right side, this is rotating in left side. So in this video we discussed the registers available in digital electronics. Register is nothing but a storage element made up of flip-flop. Flip-flop is the storage element. So it is also used for shifting the data, storing the data as well as shifting the data. Right. In that there are various types: serial in, serial out, serial in, parallel out, parallel in, parallel out, parallel in, serial out. These are the 4 types. Then bidirectional also, left to right side, right to left side. Then rotational, rotating left side and rotating right side. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the digital register. The type is serial input and serial output, SISO. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The type is serial input and serial output, SISO type of register. Then we know that the register is made up of a flip-flop. Flip-flop is the temporary storage device. So it will store the 1-bit data. Now first we will see the block diagram. Block diagram of the serial input and serial output, SISO digital register. So there are 4 registers available. It's made up of the D flip-flop. Flip-flop 3, 2, 1 and 0. These 3, this serial input, the data is sent by serially and it is passing through serial also, and output also taken as serial. The data input is serial as well as the data output also serial. So that this is the D input, this is the output, present state. The clock pulse is given to all the flip-flop. What is the nature of the D flip-flop? The D flip-flop, the input is D, is Qn is the present state, Qn plus 1 is the next state. Right? D is the one. D flip-flop having only one input. The output is present state, next state. So this next state, normally in flip-flop, the next state is depends upon present state and input. But in case of D flip-flop, whatever may be the present state, the D value will be reflected as the next state. Suppose D is 0 means Qn plus 1 will be 0. D is 1 means Qn plus 1 will be 1. Whatever may be Qn, it may be 0 or 1, whatever the value what is available here will be reflected in Qn plus 1. That is, next state is depends upon only the D input. It will not bother about the previous state. That is the nature of the D flip-flop. So whatever may be the data we are sending, the D, if the D is 1, D3 is 1 means Q3 also 1. The D3 is 0 means Q3 also 0. So that we are easily passing the data, right? So the next state value is purely depends upon the D input. It will not bother about the previous state. That is the nature of the D flip-flop, right? So we have flip-flop 0, 1, 2 and 3. Totally 4 flip-flops are available. Now we'll see the description. In all the flip-flop, be initially in the reset condition. That is Q3, Q2, Q1, Q0 is 0. Reset condition. It is 0. If an entry of the 4-bit binary number 111 is made to the register, we need to store the data 111. 4 ones need to store in the 4 flip-flop. This number should be applied to D in input. D in is the first input with LSB bit applied first. The D input of flip-flop 3 is D3 is connected in the serial data input. D in. The output of F of 3, Q3 is connected to the input of the next flip-flop D2 and so on. That is, the data is applied to the flip-flop 3. The output of flip-flop 3, Q3, is applied to flip-flop 2, second flip-flop. Then output of second flip-flop applied to the third. Like that it is going, right? The data input is given to first flip-flop. Output of first flip-flop is given to second, thereby third, fourth, like that. That is the order. Now we'll see the what happened if the data is given to the flip-flop. Now we'll see the detailed diagram. So the data what we need to store is 1, 1, 1, 1, right? So this is the data in. Data in is given to the D3, flip-flop 3. Output of Q3 is given to D2. Output of Q2 is given to D1. Output of Q1 due to D0. Finally, Q0 is the output. Right. So the initially it is 0. All the output of all the flip-flops are 0. The data what we need to store is 1, 1, 1, 1. Right. 4 ones. Right. So initially we are applying 1 to the D in. So step 1 we are applying 1 to the D3. What happened? This D3 will be available in Q3. Initially it is 1. This 0 will be applied to the next flip-flop. This 0 applied to the next flip-flop. This 0 applied to the next flip-flop. The data will move. Initially all are 0. When 1 is applied, the 1 will be appear in the Q3. The already available data 0 is moved to Q2 like that. Right? So we are applying 1. So that this 0 will appear to the next flip-flop. This 0 applied to the next flip-flop. This 0 applied to next flip-flop. The data is moving in forward direction. In step 2, again one more 1 is applied. What happened? This 1 will go to the next flip-flop. This 0 go to the next flip-flop. This 0 go to the next flip-flop. So that it become 1, 1, 0, 0. Initially 0, 0, all 0, 0. While applying only 1, it become 1, 0, 0, 0. While applying next one, it become 1, 1, 0, 0. That is data is moving one by one. Again one more is 1 is applied to the D in. What happened? This one will go to the next flip-flop. This one go to the next flip-flop. This 0 go to the next flip-flop. Now it become 1, 1, 1, 0. Triple 1, 0. Again one more 1 is applied because we need to store 1, 1, 1, 1. What happened? This one will go to the next flip-flop. This one go to the next flip-flop. This one go to the next flip-flop. So that finally it become 1, 1, 1. After 4 steps, we got our required data 1, 1, 1. That is our required data. We need to store 1, 1, 1, 1 in all the 4 flip-flop. Right? So we already discussed D flip-flop. The D input will reflected in the Q. Right? So initially all are 0. First only 1 is applied. Then it become 1, 0, 0, 0. One more 1 is applied. What happened? This one will go to next step. This 0 go to next step. Like that it will move. So it become 1, 1, 0, 0. Again one more 1 is applied. So that the outputs are moving. So it become 1, 1, 1, 1. In step 4 while applying one more 1, all become 1. So finally we got this required data 1, 1, 1 will be stored. Right? I will see the description for further understanding. Before application of signal, class signal, Q3, Q2, Q1, Q0 is 0, 0. And apply LSB bit of number to be entered in D in. Right? That so D in equal to D3 equal to 1. So on the first step, initially all are 0. In the first step, we are applying D3 as 1. Apply the clock pulse on the first falling edge of the clock. FF flip-flop 3 is set to and store the data in the format 0, 1, 0, 0, 0. That is Q3, Q2, Q1, Q0 will be 1, 0, 0, 0. Initially, all are 0. When the D in is applied to the third flip-flop, D3 is 1. While applying the clock pulse, the flip-flop is set and the data now become 1, 0, 0, 0. Now we'll see what will happen in the next step. So while applying the next bit to D in, next bit also 1. So D in is 1. As soon as the next negative edge of the clock pulse, F of 2 will be set and the stored data will be 1, 1, 0, 0. Right? The data from the F of 3 is applied to F of 2, that will set. So it become 1, 1, 0, 0. Then apply the next bit to be stored. Next bit also 1. This 1 is applied to D in. Apply the clock pulse. As soon as the third negative edge of the clock pulse, F of 1 will be set and the output will be modified to 1, 1, 1, 0. Now the data become 1, 1, 1, 0. Similarly, when D in is 1, with the fourth negative clock pulse arrived, the stored data will be 1, 1, 1, 1. Right, finally we got the required data. Now we'll see the truth table. For the further understanding, we will refer the truth table. So the data what we need to store is 1111. It's the clock pulse, the D in, that is Q3, flip-flop 3. Q3 is applied to D2. Q2 applied to D2. Q1 applied to D1. Finally Q0. So the initially all the values are 0, 0, 0. In the step 1, during the first clock pulse, 1 is applied. So this 1 is goes to the Q3. The data available here is moved to the next flip-flop. So it becomes this 0 is applied here, this 0 is applied, this 0 is applied. So it becomes 1, 0, 0, 0. In the step 2, one more 1 is applied. So that will go to the Q3. The what is available already Q3 will go to Q2. This D2 will go to D1. D1 will go to D0. So it becomes 1, 1, 0, 0. In step 3 again one more 1 is applied. So it will go to Q3. This already data what is available. Q3 will go to Q2. D2 will go to D1. Then D1 will go to Q0. So it becomes 1, 1, 1, 0. Again in step 4 one more 1 is applied because our data is 1, 1, 1, 1. So this one will go to Q3. The Q3 what is already available will go to Q2. Q2 will go to Q1. Q1 will go to Q0. So that 1, 1, 1, 1. Finally we got the data. So this is the direction of data travel. While applying 1, the data are moved to the next position. Right. That is. So finally we got the required output. Now we'll see the waveform. How the clock pulses are applied, how the data are moved. So this is the waveform clock pulse. 1, 2, 3. We have 4 data we need to store. 1, 1, 1, 4 bit. So 4 clock pulse is there. So this is the stored data. The D in initially 0. Q3, Q2, Q1 all are 0 only. Right. After during the first clock pulse, the D in is applied. So initially it is 0, 0, 0. During first clock pulse, the D in is applied. Data 1 is applied. So it becomes 1, 0, 0, 0. In Q2, this 1 will be now applied here. So during second clock pulse, the Q2 become higher. This Q3 is already higher on high level. Q3 is already high level. After second clock pulse, Q2 become high level. So 1, 1, 0, 0. In Q1, during the third clock pulse, it become higher. This Q3, Q2 already in high level. Thereafter it is high level only. So now become 1, 1, 1, 0. After applying the fourth clock pulse, Q3 also high level. Q1, Q2, Q3 already in high level. So it is 1, 1, 1, 1. Right? So the first is 1 is applied to Q3, it become high level. After clock pulse, this Q3 is transferred to Q2. So this also become high level. Now this Q2 is transferred to Q1. So Q1 also high level. Q1 is transferred to Q0. So that also high level. Right? So the data what we need to store is available. 1, 1, 1, 1. So in this video we discuss the serial input, serial output digital register, how the data are stored. We see the description, basic block diagram. It is constructed using the D flip-flop. D flip-flop nature is the D input will be reflected in the next state of the flip-flop. Whatever may be the present state, D0 means next state will be 0. D1 means next state will be 1. So that will be very useful for transferring the data. When the 1 is applied, the output of flip-flop is 1. When 0 is applied, the output of flip-flop is 0. So the data what we require is passed to the input of the flip-flop. The same data is available at the output, because D flip-flop, the output next state is depends upon the D input. D input will be reflected as the next state. Then we discuss how the data is moving in the basic block diagram. We discuss truth table and waveform also. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers, in this video we'll see the digital register. The type is serial in parallel out, SIPO type of register. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, serial in parallel out digital register. In serial in parallel out register, the data input is given bit by bit serially. We are passing the data serially. For each clock pulse, the input data at all the flip-flop can be shifted by a single position. The output at every flip-flop can be received parallelly. So here we are using the flip-flop. So flip-flop is the temporary storage device. By using flip-flop, we constructed the register. The data is given serially, bit by bit. For every clock pulse, the flip-flop is resetted. The data is changed. Because of parallel output, we are taking the data in a parallel manner. Now we'll see the block diagram. So this is the block diagram of the serial in parallel out flip-flop register. There are 4 flip-flops available, so we can store 4 bit of data. We are using the D flip-flop. What is the nature of the D flip-flop? The D flip-flop is the input D, Qn plus 1. So this is the input to the flip-flop. The present state. Qn plus 1 is next state. For a D flip-flop, whatever may be the present state, the D input will be reflected in the next state. Whatever may be the present state. If the D is 0, the next state also 0. If D is 1, next state is 1. The same input what is reflected as a next state of the flip-flop, whatever may be the present state. So that will be very useful for transferring the data. The data what we are sending is same thing will be available at the output of the flip-flop. If you send 1, 1 will be available in QA. If you send 0, 0 will be available in QA, whatever may be the previous case. That is the nature of the D flip-flop. The next state is purely depends upon the input. It is not depends upon the previous state. Right. So based on that, we are constructed the register using 4 flip-flop. Flip-flop 1, 2, 3 and 4. It is termed as A. DA, QA, DB, QB, DC, QC, DD and QD. The data is given serially. Input is given serially, bit by bit serially. The taken as output as parallelly. QA, QB, QC, QD parallelly. Right. The data we need to transfer is 1101. We need to transfer the data 1101. Right. See this, initially all this flip-flop is reset 000. The output of all the flip-flop is 000. In step 1, we are sending the data 1. For a input is 1. What will happen? If the input is 1, the data will be transferred. This 0 will be transferred to next flip-flop. Right? The 0 what is available go to, the 0 what is available QA will go to QB. The 0 available in QB will go to QC. 0 available QC will go to QD. That is, the data will be transferred. So it become 1000 in the first clock pulse. In the second clock pulse, we are sending again 0. We are sending data input as 0. What will happen? This 1 will transfer to the next flip-flop. This 0 will transfer to the next flip-flop. This 0 transfer to the next flip-flop. So what will happen here? 0, 1, 0, 0. After applying the second flip-flop, second step, the data become like this, 0, 1, 0, 0. In the third step, we are sending 1 again because the data is 10, 10, 11. So the 1. So the 1 is given in the third clock pulse. What happened? This 0 will transfer to the next flip-flop. This 0 transfer to the next flip-flop. This one transfer to next flip-flop. This 0 transfer to next flip-flop. Now it become 1010. After applying the third clock pulse, third data, the status become 1010. The fourth step again we are sending 1. 1 as the data. Right. So the QA become 1. What is available in QA? It goes to the next flip-flop. This 0 goes to next flip-flop. This 1 goes to next flip-flop. So it become 1101. So So that is our required data 1101, right? So after 4 step, the data what we need to transfer is available as the output of the flip-flop. So initially all are 0. The first step, this 1 is transferred. While transferring the 1, this data what is available QA will go to DB, QB will go to DC, QC will go to DD. Like that the data will moving. Again we are sending 1, 0. At the time this 1 will go to the next stage. Again we are applying 1. This 0 will goes to next state. 1, 1 position shifted. Again applying 1. This 1 0, this one are shifted. So finally we got 1, 1, 0, 1. Right. Now we'll see the description. In SIPO shift register is shown below. The circuit can be built with a 4 D flip-flop which are connected as shown in the diagram. Serially it is connected. Where the clock signal is given additionally to the clock signal to the all flip-flop to reset. The first. So here the clear signal also available in the diagram apart from the clock signal. The first flip-flop output is given to the second flip-flop input. Like that the 4 flip-flops are connected in serially. Right. See the diagram here. So the clear, here the clear input also available. Right. Now we'll see the 4, we are applying 4 clock pulse, we will see the detail. Initially all the output will be 0. So without clock pulse all the data become 0. Let take the 4-bit data is 1101. If we apply the first clock pulse 1 to the first flip-flop, the data to be entered into the flip-flop. Right? Initially all are 0. The data what we need to transfer is 1101. So that during the first clock pulse we are sending the data 1. So that will enter into the first flip-flop. So QA become 1 and the remaining all outputs are QA, QB, QC, QD will be 0. So we got 1, 0, 0, 0. If we apply the second clock pulse 0 because the data is 0 to the first flip-flop, then it become 0. The data already available in QA is transferred to QB, so it become 1. QC and QD already 0, so it becomes 0, 1, 0, 0. If we apply the third clock pulse as a 1 because the data is we need 1, 1, 0, 1, 1, 1, 1, 0, 1. So we are applying third clock pulses 1. So what happened? Again QA become 1, QB what is available in QA already 0 will become QB become 0. Now QC become 1 and QD become 0. The data will be 1, 0, 0, 1, 0, 1, 0. So while applying the fourth clock pulse as a 1, what happened? Again the data is shifted. QA become 1, QB become 1, QC become 0, QD become 1. One step is moving. So the fourth data output will become 1101. So the required data is available at the output. Right? So what we discussed in the diagram, it is given in the description. Now we'll see the truth table. The data what we need to store is 1101. So initially all the outputs are 0. The first clock pulse we are applying 1. This starting from LSB. First we need to apply 1, 0, 1, 1. So first 1 is applied. What happened? This QA become 1. The data what is available, the other remainings are 0. The remaining data are 0. In the second step the 0 is applied. The 0. So this one will move to the next flip-flop. The 0 move to the next. The 0 move to the next flip-flop. So now it becomes 0, 1, 0, 0. In the third step we need to apply the third digit 1. So QA become 1. What happened? The previously available QA 0 is transferred to next flip-flop. This one transferred to next flip-flop. This 0 transferred to next flip-flop. So it become 1, 0, 1, 0. In the fourth clock pulse we are applying the fourth digit 1. So QA become 1 now. The already available QA 1 is transferred to the next flip-flop. This 0 transferred to next. This 1 transferred to next flip-flop. So finally we have 1, 1, 0, 1. So that is our required output. Right. So initially 0 we are sending this data. First 1, 0, then 1, then 1. First is 1, 0, 1, 1. While applying the bits one by one, the data are moving to the next flip-flop. It is shifted. So finally we got 1, 1, 0, 1. Now we'll see the waveform. Clock pulse along with the 4 different output. So this is the waveform is available. This clock pulse is there. So we are applying the 4 clock pulse. 1, 2, 1, 2, 3, 4. Initially all are 0. So first we are applying QA as 1. So that the data what we need to transfer is 1, 0, 1, 1 starting from LSB. Right. So 1, 0, 1, 1. First 1 is applied. So it become 1, 0, 1, 0. Right. So after that this 1 will be transferred to the next. This 0 is shifted. Now become 0, 1, 0, 0. Right. After third clock pulse, this 0 will be shifted. So it becomes 0, 0, 1, 0. Right. And fourth, this 0 will be transferred. Now 0, 0, 0, 1. So this is our record output. 1, 1, 0, 1. This is the LSB. 1, 0, 1, 1 will be available at the output. Right. So after applying the 4 clock pulses, the data is moving. This 1, initially 1, that 1 is transferred to the next. And also the next. Is keep on serially while applying the clock pulse. This 1 is keep on transferring. This 0 also keep on transferring. This 1 also transferring. Finally this 1. So 1, 0, 1, 1 will be available at the output. So our record output is 1, 0, 1, 1. That is our, this is LSB. This is MSB. Right? The MSB stored in QA, LSB stored in QD. So in this video we discussed the serial in parallel out register. We discussed the block diagram. We discussed how the data is transferred. We taken the sample data 1, 1, 0, 1. We are applying the data one by one. 1, 0, 1, 1. Then how it is moving we discussed. And also we discussed the truth table and waveform. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Some viewers, in this video will see the digital register. The type is parallel in serial out, PISO. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, parallel in serial out digital register. The shift register uses parallel input and generates serial output is known as parallel input serial output shift register. The data is given parallelly and taking the output as serially. This shift register work in a reverse way of SIPO, serial input parallel output. Here what we have, parallel input serial output. So it is reversed. In this type of shift register, the input data enters a parallel way and come out serially. But in SIPO, the data goes serially and taken out parallelly. So the input of second flip-flop is the output of the first flip-flop, right? So from first flip-flop, the data will given to the second flip-flop. Right. Now we'll go to the logical diagram for this parallel in serial out shift registers. Right. See here there are four D flip-flop available. 1, 2, 3, 4. It is constructed with the 4 D flip-flop. What is the excitation table of the D flip-flop? The D flip-flop, the input D, present state, next state, Qn plus 1. What is the nature? The whatever may be the present state, the input what we are applied D will be reflected as the next state of the flip-flop. For example, if D equal to 0, whatever may be present state, the next state will be 0. Suppose D equal to 1, whatever may be the present state, the next state will be 1. Right? So D0 means the output of the flip-flop, D flip-flop is 0. D1 means the output of the flip-flop will be 1. The input will be reflected as the next state of the flip-flop, not bothering about the present state. So that we are using D flip-flop for converting the register. The data what we are entered, D input, same thing will be available at the output. So that we can easily use the loading the data, shifting the data, parallelly we can pass the data, or serially we can pass the data. Input will be reflected at the output. So that is the main reason we are using the D flip-flop, right? So here the flip-flop A, B, C, D. These are inputs DA, DB, DC and DD. The outputs are QA, QB, QC and QD. These four outputs. So what we are giving, DA will be available as QA, DB will be available as QB, right? So because of parallel input and serial output, there are two modes available. We can parallelly load the data one time, or we can shift the data, shifting from one flip-flop to another flip-flop. So two possible operation is available in this type, that is shifting the data from one flip-flop to another flip-flop and loading the data parallelly. So that is controlled by this logic circuit. Two AND gates and one OR gate is available, right? This. And also the mode 0, 1, right? Based on the mode, it will act as a shifting or load. See here, one line is available here. The AND gate is connected. In this and in this line, this AND gate G1, G2, G3 are connected. In this normal line, G4, G5, G6 are connected, right? Both are connected by OR gate. Nature of OR gate is any one is high, it will give the high output, right? Now we'll see what will happen if it is 0. This is the control line. It will decide whether the shifting or loading. Suppose 0 means after the NOT gate here 1. This line will be 0. Same thing will be 0. Due to 0, G4, G5, G6 will be 0 only, disabled. It will not give any output because of AND gate. Only this line is having a digitally logical high output. So that is connected to G1, G2, G3. So it will get the high output. One input is high. What is the another input? B. The data B, data C and data D. The A is already given in the DA. So it is nothing but a parallel loading. So one input is high, another input is input data. So this will be either high or low based on the data. B equal to 0 means this will be low. B also 1 means high. So that will be given to this OR gate. So this will give the data to the DB. So the parallelly loading the data. Similarly, this D2 will load the data C to the DC. Similarly, this G3 load the data D to the DD, right? So the parallel loading will happen. A will be loaded here, B will be loaded through G1 and this OR gate to DB, C will be loaded through G2 and OR gate to the DC, D will be loaded through the G3 and this OR gate to the DD. The data will be parallelly loaded because G1, G2, G3 are having high input because of 0. Here 1. So 1 will enable this G1, G2, G3 AND gates. This line is 0. So G4, G5, G6 is disabled. Right. Suppose if the line is 1. Suppose this input is 1. So what happened here? It become 0. So this line will be disabled. So G1, G2, G3 will be disabled. We cannot load the data. Here the line is 1. The second line now become 1. That is connected to G4, G5, G6. Right. See what is the next input to this? See this. It is from DA. Right. The data is given. The output available here, that is given to another input of the G4. So this G4 is connected through this OR gate to the next flip-flop. So the meaning is shifting. The data what we entered DA, that is available in QA, that will go to G4. Already here 1 is there. Already this AND gate is enabled. This is disabled because of 0. So that will go to OR gate. Through the OR gate it will go to DB. So the QA will be shifted to DB. Similarly, QB will be shifted to DC through this G5 and OR gate. Similarly, this QC is shifted to DD through this G6 and this OR gate. So the shifting will happen. If the input is control, input is 1, shifting will happen. The control input is 0, after this line it become 1, then parallel loading will happen, right? So we can control the operation either shifting or loading based on this value. 0 means parallel loading, 1 means shifting the data, right? So it is clearly we are able to understand by using the diagram, right? So the loading, this line is high, so here G1 is enabled, we are connecting the data here, so it is parallelly loaded. 1 means this line is enabled here, or this line is enabled. One more input is from first flip-flop will shifted to second flip-flop, so the shifting will happen, right? 0 parallel loading, 1 shifting the data from first flip-flop to second flip-flop, right? So this is the serial data output. Now we'll see the description as well as the waveform and truth table. So what we discussed now, it is given as a description. The bits A, B, C and D are passed to the corresponding flip-flop when G1, G2, G3 are AND gates are active. This is the first mode. 0 means after the NOT gate, this G1, G2, G3 got high outputs. These gates are active when the load shift line is set to 0. The binary inputs A, B, C will be loaded to the respective flip-flop when the edge of the clock is low. Thus parallel loading occurs, right? If the control line is 0, G1, G2, G3 are active, this data ABC is connected as another input of G2, G3, so the data will be parallelly loading. The G4, G5, G6 AND gates will be activated when the shift load line is set to 1. When, right? If it is 1 means it will go for the shifting mode. The shifting of data will be left to right bit. In this way, parallel in serial out operation will occur, right? So 0 means parallel loading, 1 means shifting. Now we'll see the truth table for both. Shift or load control is 0 means it is a parallel loading. The data is 1, 1, 1. So through the AND gate and OR gate G1, G2, G3, this data D1, 1, 1, 0, 1 is transferred to DA, DB, DC and DD. Right? DA will get 1, DB will get 1, DC is 0 and DD will be 0. Right? Through the NOT gates G1, G2, G3, the data is parallelly loaded. Now the shift or load control is 1 when the clock pulse is applied. Now what happens? Shifting. Now the data will be shifted. G4, G5, G6 AND gate will be enabled. Will be got the high output. Now we'll see how the data will be shifted. Right. So the initially all the data are 0. Output of the flip-flop QA, QB, QC are 0. In the first clock pulse we are applying 1. The data what we need to apply, what we need is 1, 1, 0, 1. First we are applying 1 to the first flip-flop. So it become 1, 0, 0, 0. The DA what we are applied will be available at the QA. QA will, output will be 1, other outputs are 0. While applying the second clock pulse, the data will be shifted. QA is given to the DB of the next flip-flop. So the same DB available as the output of QB, right? So that QA is transferred to QB. This 0 is transferred to third flip-flop. This 0 is transferred to fourth flip-flop. Now what happened? It become 1, 1, 0, 0. After the next clock pulse, we are passing 0 because the third digit is 0. Now what will happen? This 1 will be shifted to second flip-flop. This 1 shifted to third flip-flop. This 0 shifted to fourth flip-flop. Now the data becomes 0, 1, 1, 0. Right. Now in the fourth pulse we are applying 1. This fourth data is 1. Now what will happen? This 0 shifted to second flip-flop. This 1 shifted to third flip-flop. This 1 shifted to fourth flip-flop. So finally what we have? 1, 0, 1, 1. That is 1, 1, 1, 1, 0, 1. Starting from the MSB we can write 1, 1, 0, 1 as the output. Is shifted. The data while applying the clock pulse 1 by 1, the data is shifted. We are applying what we need data. 1, 1, 0 is applied step by step. While applying the clock pulse, it goes to the next stage. Now we'll see the timing diagram. So there are 4 digits available. So 4 clock pulse. 1, 2, 3, 4. Initially all are 0. During the first clock pulse, QA we are passing the data 1. Right. The second clock pulse we are passing the data again 1. This 1 is shifted here. These zeros are shifted. The third clock pulse we are applying again 0. So this one shifted here, this one shifted here, this 0 shifted here. Right. Finally we are applying again 1. What we need is 1, 1, 0, 1. Right. So this 0 is shifted, this one is shifted here, this one is shifted here. So final data what we have 1, 0, 1, 1. That is 1, 1, 0, 1. So in this video we discuss about the parallel in serial out type of digital registers. We discuss the logical diagram. In that two modes available, parallel loading as well as shifting, that is controlled by one NOT gate, and logic diagram. 2 AND gate, 1 OR gate will control the operation, either loading or shifting based on the value. 0 means parallel loading, 1 means shifting. Then we discuss the truth table for both loading and shifting. Then we discuss the waveform also, clock diagram. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the digital register parallel in and parallel out type. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Digital register, the type is parallel in and parallel out. Data is given parallelly and taken also in parallelly. The shift register uses parallel input and parallel output is known as parallel input, parallel output shift registers. This shift register include 3 connections only: the parallel input, parallel output and clock pulse. The data is given parallelly, taken as parallelly, using also it uses the clock pulses. This kind of shift register also work like a time delay device or temporary storage device like SISO shift register, with the time delay being changed through the clock signal frequently. So we are giving input parallelly, taking the output parallelly. So by using the time delay we can take it as a time delay device. By using the clock pulse we can make it as time delay device, because parallel input, parallel out, nothing will be there. So by using the clock pulse we can use a delay. Also we can temporarily we can store the device also. Now we'll refer the circuit diagram. So this is a circuit diagram. This this register constructed by the D flip-flop. It is constructed by D flip-flop. There are 4 flip-flops available. This is a clock pulse. This is a D input and QA output. Right. In this D flip-flop, what is the nature of the D flip-flop? The input D, present state, next state. So in D flip-flop, the next state is depends upon the input D value. It will not depends upon the present state. Whatever may be the present state, the input will be reflected in the output, next state of the D flip-flop. Suppose for D equal to 0, whatever may be the present state, the next state also 0. D equal to 1, whatever may be the present state, the next state will be 1. D0 means next state will be 0. D1 means next state will be 1, whatever may be the present state. So that is the advantage with we are using the digital register. So what is the data we are entering, input, will be available at the output. Input and output both are same. The input what we are applied will be reflected at the next state of the flip-flop. That's why we are using the D flip-flop to construct the shift registers. Here 4 registers, 4 flip-flop available. Flip-flop 1, 2, 3 and 4. So this is the data given parallelly. All 4 flip-flops we are supplying the data parallelly. Similarly, the output is also taken as parallel. QA, QB, QC and QD is the 4 parallel outputs. So let us consider we are going to use the data 1101. Right? We are going to use the data 1101. Initially, all the inputs are 0. Ensure all the inputs are 0. Then we are parallelly we are applying DA as 1, DB as 1, DC as 0, DD as 1, because what we need is 1 1 0 1. What data we need, that is given to the respective inputs of the D flip-flop. The same thing will be available at the output. QA will be 1. DA 1 means QA also 1. DB is 1 means QB also 1. DC is 0 means QC also 0. TD is 0, 1 means QD also 1. Right? So parallelly we are giving the data, parallelly we are taking the data. So that is done by the clock pulse. So by using the clock pulse, we can make this device as a time delay device. If the clock pulse duration is very long, mean time delay. Delay between input and output. And also it can be used as a storage. We can store the data in these 4 devices, 4 flip-flop. Right? The circuit operation is simple. What we are supplying, that will be available at the output. That is the nature of the D flip-flop. The input will be reflected at the next stage of the flip-flop, whatever may be the present state. I will see the description of this circuit. The circuit diagram of parallel in, parallel output shift register is shown below. The input allowed by this type of shift register is parallel and gives the parallel output. Input also parallel, output also parallel. This logic circuit is designed with a 4 D flip-flop as shown in the diagram. We know that 4 flip-flop D type. So input and output will be same. For that we are using the D flip-flop. Right. Some more description available. There is no interconnection between the individual flip-flop. All are individually connected. There is no interconnection because no serial data shifting is necessary. Right. There is no interconnection. Right. So data enters here and data leaves here. Data enters and data leaves. There is no interconnection. Only the clock pulse is interconnected. Now we'll see the some more description and logical table. If we take the input is 1101, which is loaded in each flip-flop, 1101. Initially the output will become 0. Initially it is 0. If you apply the first clock pulse, then the data will be shifted from input DA to QA, DB to QB, DC to QC, and DD to QD, so that the output will be 1101. While applying 1101, after the first clock pulse, this data will be, the input will be available at the output, so that we will get 1101 as a output. This truth table is available. Clock pulse 0, clock pulse 0. Initially we are applying 0 0, all are 0 0. In the first clock pulse, the input is given. This 1101 is loaded in the flip-flop. So that same thing will be reflected as the output. QA is 1, QB is 1, QC is 0, QD is 1. Right? After applied the first clock pulse, the output will be reflected at the output. Now we will see the waveform clock pulse. So this is the clock pulse. Initially all are 0. QA, QB, QC all are 0. After the first clock pulse, the DA, the flip-flop, first flip-flop will got 1. Second flip-flop also 1. Third flip-flop 0. Fourth flip-flop 1. So this QA will be higher, QB will be higher, QC is lower because of 0. QD will be 1. After the first clock pulse, the same thing will be reflected at the output. 1101 is the data what we are transfer, or the data what we are storing. So in this video we discuss parallel in, parallel out type of shift register. The circuit diagram constructed with the D flip-flop. The input what we applied, that will be reflected at the output. So due to that we are using D flip-flop for the constructing the register. And we discuss the truth table as well as waveform. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we'll see the digital register. The type is bidirectional shift register. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, bidirectional shift register. we'll see what is meant by bidirectional shift register. If a binary number is shifted left by one position, then it is equivalent to multiplying the original number by 2. So while shifting left side by 1 bit, it is equivalent to multiplication by 2. Similarly, if a binary number is shifted right by one position, then it is equivalent to dividing the original number by 2. Right? So the left side means multiplied by 2, right side means divided by 2. So by using this bidirectional shift register, we can move the data either left side or right side. So that is equivalent to multiplication or division. So for that purpose, we are using this universal, using the bidirectional shift register. I will see the further details. Here, if you want to use the shift register to multiply or divide, then the binary number, given binary number, then we should be able to move the data either in left or right direction. In order to perform the multiplication or division, we need to move the data either in left side or right side. Such a register is called a bidirectional register. A 4-bit bidirectional register we will consider. We will consider the 4-bit bidirectional shift register. So there are two serial inputs, namely serial right shift data DR, serial left shift data DL, along with the mode selection M, along with the mode selection M. We will see the diagram. So we have DR, data right shift, DL, data left shift. In order to select this, we have mode control. Now we'll see the diagram, logic diagram. So this is the logic diagram of the universal is a bidirectional shift register. Bidirectional shift register. So there are 4 flip-flops available. Flip-flop 0, 1, 2, 3. There are 4 flip-flop available. This is the clock signal. Clock signal is given to all the flip-flop. Right. So here we used the D flip-flop. What is the nature of the D flip-flop? Why we are using the D flip-flop? The D flip-flop, we know that the input is D, the next present state is Qn, next state is Qn plus 1. Suppose the D is 0, whatever may be the present state, the same 0 will be available as the next state. If D is 1, whatever may be the present state, the same 1 will be available as the output. So whatever may be the present state, D will be reflected. The value of D will be reflected at the next state of the flip-flop. So that if we pass the data 0 to the input of the flip-flop, the same 0 available at the output. If we pass the data 1, the same data 1 is available at the output. So that we can easily shift the data from right side to left side or left side to right side, or we can pass serially, parallelly, all are possible, because what we are sending, the same thing available at the output. If you pass 1 at this D3, Q3 also 1. If D3 is 0, Q3 also 0. So there is no change. So that can be, so the property of the D flip-flop such that same, input and output same, so that we are using the D flip-flop for the register, digital register, for sending the data serially or parallelly, shifting right, left, everything, we are using D flip-flop. Right. Now we discuss about the D flip-flop. Now we'll see how to control the data left side or right side. See this. Here one control, mode control is available. Mode selection. And one more NOT gate is connected, so that M bar is available in this line. The first line we have mode signal M. Second line we have mode signal M bar. M0 means M bar will be 1. M1 means M bar will be 0. Right. Now we have the logic diagram is available here. Two AND gates and one OR gate. It is named as 1, 2, 3, 4, 5, 6, 7, 8. Right. Now we'll see what will happen if it is right shift or left shift. Right. So this, the right shift data is entered at this point, DR input. The DL input is entered at this point to the AND gate 8. DR input is given to the AND gate 1. right? Now we'll see what will happen. If m equal to 1, if m equal to 1 means this line will be logically high, this time will be logically low, right? So in this line we are connected the 3, the AND gate 3, 5, 7, then 1. 1, 3, 5, 7 are connected, right? So 1, 3, 5, 7 will be activated. 2, 4, 6, 8 will be deactivated. See this, the left side data we cannot go for, this deactivated. 1 is activated, so the right side, shift left, shift right is possible. So the data is entered here, this is already high, so that is goes to the OR gate. OR gate nature is any one is high, it will be high. So the data will be passed to the first flip flop, right? So the M is high level, so the AND gate 1 is activated. The data what we need to shift right side is given to the AND gate 1. Based on the value, it is goes to OR gate. Then OR gate value goes to D. Either 0 or 1, that will pass to D3. The same thing will be available at the output of flip flop Q3. This Q3 is given to the AND gate 3, right? This 3 also connected to high level. So this is activated. So that input is given to second flip flop. Then output of second flip flop is given to the fifth AND gate. So this is also already activated. 1, 3, 5, 7 is activated. From 5 it is given to the third flip flop, input of third flip flop. Output of third flip flop is given to the AND gate 7. From that it is given to fourth flip flop, right? So now the data is shifted right side. Data available here, that is passed to the first flip flop. Output of first flip flop is goes to AND gate 3, that is passed to second flip flop. Second flip flop output goes to AND gate 5, that is passed to third flip flop input. Third flip flop output is goes to AND gate 7, that is given to the fourth flip flop input. Then it is goes, just keep on going, right? So the data is shifted right side. Suppose if the M is 0, what happened? This line is deactivated, that is 1, 3, 5, 7 AND gates are deactivated. Here 0 means M bar will be 1. So this line will be now activated. What is that? The AND gate 2, 4, 6, 8 are activated now, even numbers 2, 4, 6, 8, right? So in the 8th gate we are giving the data which is want to shift left side. Now we given the data this side, now we are giving the data this side, left side. So the data is entered into the AND gate 8. From that it goes to OR gate, then data is given to the fourth flip flop. Now this, if we consider 1, 2, 3, 4, this is the fourth flip flop. The output of this fourth flip flop is given to sixth AND gate. So this is also already activated. From that it is given to third flip flop input. Output of third flip flop is given to AND gate 4. From that it is given to second flip flop input. Then output of second flip flop is given to the AND gate 2. From that it is given to first flip flop. Then this output again goes to the next step, right? So from this side the input is goes to AND gate 8, then flip flop 4. Output of flip flop goes to AND gate 6, then it goes to third flip flop. Output of third flip flop goes to AND gate 4. From that it goes to second flip flop. Output of second flip flop goes to AND gate 2. From that it goes to flip flop input of the first flip flop. Now the data is shifted left side, right? So based on the M value, either we can shift the data right side or left side. M is 0 means the data entered from this point and shifted right side. M is 0 means this line is activated, data is entered here and shifted left side, right? Now we'll see the description. Now we'll see the logic operation of this logical diagram. First case, when M equal to 1, we can perform shift right operation. That is, if M equal to 1, then the AND gates 1, 3, 5 and 7 are enabled, whereas the remaining AND gates 2, 4, 6, 8 and 8 are disabled, right? The data is entered at DR is shifted to the right bit by bit from flip-flop 3 to flip-flop 0. That is first flip-flop to fourth flip-flop on the application of clock pulse. Thus, with m equal to 1, will get the serial right shift operation. Similarly, if m equal to 0, what will happen? If m equal to 0, we can perform shift left operation. When the mode control m is connected to 0, then the AND gate 2, 4, 6 and 8 are enabled due to NOT gate is connected, and 1, 3, 5 and 7 are disabled. Now the data to be shifted left side DL is shifted bit by bit from F00 to F3. This is the fourth flip-flop to fourth flip-flop to first flip-flop on the application of clock pulse. Thus, with m equal to 0, we can get the serial right shift operation. So in this video, we discuss the shift register, universal shift register. We have that mode of, based on the mode control, we can shift bidirectional. We discuss the bidirectional shift register, shifting right side or left side, that is decided by the mode control. If mode m equal to 1, shift right operation, m equal to 0, shift left operation. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the digital registers. The type is universal shift registers. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, universal shift register. We'll see first what is meant by universal shift register. A shift register which can be shift the data in only one direction is called unidirectional shift register, only one direction. A shift register which can be shift the data in both the direction, right side as well as left side, is called a bidirectional shift register. Right. Applying the same logic, a shift register which can be shift the data in both direction as well as the loading it parallelly, right? Shifting right side and left side as well as parallelly loading, then it is called a universal shift register, right? Bidirectional, unidirectional means only one direction, bidirectional means both the direction, universal means both the direction as well as parallel loading. These three operation is performed, so that it is called a universal shift register. The shift register is capable of performing the following operation: parallel loading, left shifting, right shifting, right? Left shifting and right shifting, LEF, right? Now we'll see the description is available. Now first we'll see the logic diagram, then we'll go for this explanation. Now we'll see the logic diagram. So here we are using the SR flip-flop for constructing the universal shift register. This SR flip-flop. Normally we use the D flip-flop. D flip-flop for constructing the register. For example, for the D flip-flop, what is the nature? The D input, Qn next to present state and Qn plus next state. If D equal to 0, whatever may be the present state, the next state will be 0. If D equal to 1, whatever may be the present state, next state will be 1. So the input what we are giving, that will be reflected as a next state. It will not bother about the present state. So that is the advantage for register. What data we are sending, that same data will be available at the output. The flip-flop input is 0 means the flip-flop output will be 0. Flip-flop output is input is 1 means output also 1. So that we, by using this property, normally we are using D flip-flop for constructing the register, but here we are using the SR flip-flop. The R input is directly given and S input is given with the inverted input. So this is also normally similar to the D flip-flop. D flip-flop from SR flip-flop. Now we'll see how it will transfer the data. Parallelly how it will load, how it will transfer the data from left side and right side. All these things we'll discuss, right? Normally we are using D. Here we are using SR flip-flop. R input and S input is inverted, right? In order to perform the three different operations, we have the mode control. the signal M is available, and logic diagram is there. 2 AND gates and 1 NOR gate is available. It's connected to all the flip-flop, right? The 2 AND gate with 1 NOR gate set of this logic circuit is connected. In order to control the clock signal also, here we have 2 AND gate and 1 OR gate. It is used for clock right shift. This is used for clock left shift, right? Now we'll see how it will be loaded. We need to see the 3 operations: parallel input, parallel loading, shifting, serial input, shifting left side and right side as well as left side, right? First we will see if M equal to 0. If M equal to 0, here it will be 1. If M equal to 1, after the NOT gate becomes 0, again it becomes 1, right? So this line will be activated. This line is logically 0, right? The upper line is activated. In this upper line, what we are connected? The AND gate 2, 4, 6 and 8. These 2, 4, 6 and 8 are activated now. 1, 3, 5, 7 are deactivated because of 0. One input is 0 means totally it is 0. See this in 2, 4, 6, 8 we are connected the data also. A is connected, B is connected, C is connected and D is connected. So what happened? From this the data will go to this NOR gate and it will go to the flip-flop, right? So this is called a parallel loading, right? If M equal to 1, 0, then 1 means called a parallel loading, right? The data what we are enter is goes to second AND gate. Already this AND gate is connected with high level, right? So this output will be goes to NOR gate, then it will go to the flip-flop, then the output will be taken out, right? Now we'll see what will happen if the data is 1, whether we are getting the same output. If data is 1, what is the output? If data is 0, what is the output, right? If the data A equal to 1, what happened here? So this already this is 1, this input is 1 and this input also 1 means we'll get 1 as a output from the AND gate. This 1 is goes to this NOR gate. NOR gate, what will happen? 1 means the output will be 1, but because of NOR gate it is 0, right? The NOR gate, the input is 1 means output will be 0. So this 0 will be applied here. This is R is 0 and S is 1, right? R equal to 0 and S equal to 1. What happens is S equal to 1 and R equal to 0. S equal to 1 means set. Set means it will reset, it will set the output. Set the output means it is 1, right? Set the output means the output will be 1, right? The underline is the second possible operation. The normal number is the first possible, right? So this line is 1. Suppose if the A equal to 1, both due to 1 and 1, we got the AND gate output is 1. If the 1 is applied to NOR gate, the output will be 0. This 0 is applied to the R input of the SR flip-flop. Inverted input is applied to S flip-flop. So it becomes 1. R equal to 0 means S equal to 1. If S equal to 1, R equal to 0, what is the meaning? Set. S equal to 1 means set. Set means 1. Reset means 0. Set means 1. So the A equal to 1 means the same 1 will be available at the output of the flip-flop, right? Suppose A equal to 0. What happened? This line is 1 but A equal to 0. So we'll get the 0 as the output because of AND gate. 1 into 0, 0. If 0 is applied to the NOR gate, what we'll get? We'll get 1. 1 as the output. This 1 is applied to the R. One input of the SR flip-flop is R is 1. The inverted input 0 is applied to S, right? S equal to 0, R equal to 1. R equal to 1 means reset. Reset means whatever may be the present state, the next state will be resetted 0, right? So we'll get the 0 as the output. That is, if A equal to 0, the output is also 0, right? So what the data we entered here, that will be available at the output. This is applicable for all 4 flip-flop. A, B, C, D, 4 inputs are applied to the 4 flip-flop. Same thing will be available at the output as QA, QB and QC. QD, QC, QB and QA. So this is the parallel loading. It is applicable for parallel loading. Now we'll see the shift left and shift right operation. Right. If M equal to 0, this will be 1. This will be 0. So this upper line is totally disabled. This lower line will be now enabled. Lower line where we are connected 1, 3, 5 and 7. Right. This 1, 3, 5, 7 are connected. 2, 4, 6, 8 is now disabled. Right. So here we are giving the serial input. See this gate pulse also. Here what is available now, 0 means 1. 1 is connected here. Right. Here the signal is given. Here 0 is connected. So this becomes 0. So the right shift operation is performed. If we give the input here, then left shift operation will be performed. Right. Now 1, 3, 5, 7 is enabled. If we give the input here, it perform the right shift operation. If we give the input here, it will perform the left shift operation. This is the clock pulse controlling right or left. Right. If the clock pulse is 1, already here also 1. If we want to perform right shift, this clock pulse is given. Here this is 1 and this is 1. So the pulse will be given. So it will perform the right shift operation. If this clock pulse is given, here it is 0. Here it is 0, so it will not perform. Right. So while going to the left shift operation only, it will perform this value. Right. Now see how the data is shifted right side. So the data is given here. That will goes to the NOR gate and it will go to the input that is available at the output here. This is the output. So this is the output available here. In order to draw the diagram, the line is taken from this side. That is goes to third AND gate. So this is also already active. From third AND gate and NOR gate, it goes to second flip flop. Then output of second flip flop goes to fifth AND gate. From NOR gate, it goes to third flip flop. Output of third flip flop goes to seventh AND gate. Through NOR gate, it will goes to the next fourth flip flop. Like that, the data will be transferred. Similarly, if we give the input here, then it will perform the left shift operation. So we discuss right shift operation performed. In order to perform left shift operation, the diagram you have to modify. In the seventh AND gate, we need to connect the same what we are serial input. This will be given here. The diagram not possible to draw. Only right shift operation, the direction and the diagrams are clearly given. If you want to perform the left shift operation, same thing should be repeated from this side. 7 input should be given to 7, then it will pass to 5, 3 and 1. So not possible to draw the diagram, the lines will be confused. So only right shift operation, the flow of diagram is given here. So M equal to 1 means parallel loading. M equal to 0 means right shift or left shift. If the clock pulse right shift is given, it will perform right shift operation. If the clock pulse left shift is given, it will perform left shift operation. We need to modify these lines. This serial input should apply here, right? We need to redraw the diagram. So in this video, we discuss the universal shift register to perform the parallel loading, shift right, shift left, 3 different operations. Now we'll see the description available. We will see the description. So what we discuss is available. The mode control input is connected to logic 1 for parallel loading operation, whereas it is connected to 0 for serial shifting, right? 1 for parallel loading, 0 for serial shifting. When mode control pin is connected to ground, the universal shift register acts as a bidirectional register. For serial left operation, the input is applied to the serial input, whereas which goes to the AND gate 1 as shown in the diagram. Whereas for the shift right operation, the serial input should be applied to D input. So that is that direction was not given in the diagram. So shift right left operation is clearly given, right? So we can perform parallel loading shift left or shift right. These three operations we can perform. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.